Hi, welcome to our video on how to write chemical reactions for nuclear decay. We're going to start talking about alpha decay, beta decay, and gamma decay, so please take out your notebook so you can start taking notes. Okay, so our first type of radioactive decay will be alpha decay. Um, why does this happen? Remember that we're talking about a nucleus that is very big and unstable. So this nucleus, the strong nuclear force holding the protons and the neutrons together is not strong enough, and what will happen is two protons and two neutrons will be released, and this is an alpha particle. So we have here the isotopic notation for the alpha particle. We have the Greek letter alpha. And we see here, remember isotopic notation, usually for an atom, we have the atomic number on the bottom left. However, because we're not talking about atoms, this atomic number here, we're going to say it's just the number of protons or the charge that we have for this nucleus. So in this case, the 2, we don't say it's the atomic number, we say it's the number of protons, just because we're not talking about an atom. Upper left, we have the mass number. That's in this case, it's 4 because we have 2 protons and 2 neutrons. Or we can write this. This resembles a helium nucleus. So we write it with the element symbol for helium. We have 2 protons and 2 neutrons as well. So we add those for our mass number. And you notice here that we don't have a charge on the upper right. That's because this is not an atom, this is a nucleus. So alpha particles, we know from the lab, they're large and heavy, they're slow moving, they're easy to shield. So for example, your skin will be able to shield them, and their penetrating ability is poor, and that's what makes them very dangerous if you get them inside your body. So inhaling or digesting alpha particles can be very, very dangerous because they will not be able to get out. Now let's get to the fun part, the equations. When we're writing nuclear equations or nuclear reactions, we have to keep in mind two things. One is that the mass number is always conserved, and the other one is that the electrical charge is conserved. So these are two conservation laws that we have to follow all the time. We begin here with one element, that will be radium. So we have the isotope radium-226. And this radium, we see here we have 88 protons, so this is the charge that it has, and 226 will be the mass number. So here we have the neutrons included. Now it undergoes alpha decay, so that means that we have an emission of two protons and 2 neutrons. So here we have 2 protons plus 2 neutrons for our mass number. This is our alpha particle, and we have to determine um, the transformation it undergoes. So it converts itself to another element because it lost 2 protons, sorry. 88 minus 2 protons, that should give me a number of 86. So my new element that is formed after the decay should have 86 protons. So checking the periodic table, we know that the element that has 86 will be radon, and this radon, we write here the symbol. We know it has 86 protons, and then we have to check the mass. So 2 neutrons were also emitted, and on top we have the mass number. So a total number of 4 units were emitted. 226 minus 4 is 222, so that's why we have 222 here. Now you see the numbers on the left are equal to the numbers on the right. This is part of balancing equations. So if we draw a line here, we have 88 on the left, and 86 plus 2 is also 88. So this equation is balanced. Same thing for the mass number here, 226 on the left, and on the right we have 4 plus 222. So we have 226 on the right as well. So this equation is balanced, and that will be an example for alpha decay. Our next example will be spontaneous beta decay, and for this we have the emission of electrons or positrons. Remember we mentioned that a positron is a positive electron. So the isotopic notation for this ones is E for electron, and we have here the charge on the bottom. So again, this isotopic notation, we're not talking about the atomic number, but we're talking about a charge here on the not upper, on the bottom left corner. The electron, this will be a beta negative particle. And for the positron, we have a beta positive particle. If we take a look here on the top, we see that we have a number 0. That's because the mass relative to the proton or neutron, the mass for the electron will be considered 0 in this case. We know the electron does have a mass, however, it's very, very insignificant compared to the other particles inside the nucleus. So beta particles, you know already from the lab that they're small and fast. They're kind of easy to shield, so protective, for example, gloves or an aluminum foil will shield them. Their penetrating ability is medium, so they're still dangerous on the outside and on the inside of your body. Now let's take a look at how to write down the equations for beta decay. So we're going to begin with negative beta decay. So here we have hydrogen, and we have the one proton. We have three neutrons. So we see that we have more, a wrong ratio here with neutrons and protons. We have more neutrons. So one neutron will become a proton and give off an electron. So if we think about it, one of these neutrons here will be converted into an electron. So that's the first part. Here we have the electron. And remember, when you write this, you have E for electron, and it has a negative charge, and the mass will be 0. Now, we have to keep a balance here with our charges. So if we have a 1 on the left, and we have a negative 1 here, that means that we need a number 2 for a new element that is being formed. So that yields to helium. So you need a periodic table to solve this one. So you go to the periodic table and you see which element has 2 protons. That will be helium. So you write down the element symbol, and then we have to check here the mass. It has to be equal on the left and on the right side of the equation. So on the left we have 3 for our mass, and because the electron has an insignificant mass, in this case it's 0, the mass doesn't change at all. So we still have 3. And if you think about it, how come we had an electron, I mean a neutron, split into a proton and an electron? Well, here's the equation. This neutron has a charge of 0, it has a mass of 1, and we have that it converts itself into a proton that has a positive charge, mass of 1, and the electron that has a negative charge and a mass of 0. So let's check the numbers here. Let's balance this out. 0 on the left for our charges, and here +1, -1, that's still 0 on the right for charges. Then the mass, 1 on the left and 1 on the right plus 0, that's still 1. So we see that the mass and the electrical charges are conserved, and that reassures that our equation is correct. So that's one example of beta negative, and this happens when we have more neutrons than protons. For our second example, for beta decay, we have another element here. We have sodium, and this is an example of beta positive decay. In this case, we have too few neutrons for a number of protons. So this element here, what will happen is a proton will transform itself into an electron that's positive, a positron, and a neutron. So we begin first with a positive electron, and I know that's really weird and hard to visualize, but yes, we can have a positive electron, and this positive electron, we see that it has a positive charge here. So that means if we have 11 for charge and 1 here, the other element that we're forming should have a number 10 to balance our electrical charges. We're looking for an element that has an atomic number of 10. So we check the periodic table, and that will be neon. So here, make sure you're trying this too as we're going through the video. So neon has here 10 protons, and then we have to balance the mass number too. Because the electron has no mass at all, the mass number doesn't change. So it's still 22. And here we have our equation for the proton, so how it changes to a positron and a neutron. We have a proton with of course one for the charge and one for the mass, and this changes into an electron that's positive, a positron, zero mass here. So we have to balance the numbers. 1 on the bottom, so 1 plus 0, that will be a neutron here. And then on the top, we have 1 on the left, and 0 plus 1, that's 1 on the right. So mass, number, and charge is balanced. And this is how we form a positron when we have um, a wrong ratio of neutrons and protons in the nucleus. We have way too few neutrons for our nucleus. Finally, we have spontaneous gamma decay, and this is not a particle, this is a gamma ray, so it's a wave of energy. The isotopic notation is the Greek letter gamma, has zero charge and zero mass. Okay, so it's basically energy. Because it has no mass, it travels at the speed of light. It's very difficult to shield, so you would actually need a very thick concrete wall, and the penetrating ability is excellent, so gamma rays are very, very dangerous. And this is the easiest equation of all because no mass or charge is lost. So basically, we would keep the same element or the same nucleus that we started with. The only thing that is changing is the energy. Let's see our example. We have plutonium. This isotope has a mass of 245 and it has 94 protons. Because the nucleus is not losing either protons or neutrons, it will remain exactly the same. The only thing that is emitted, so let me remove this one. What we have here is that energy is emitted. A gamma ray has no charge, no mass, and we still have plutonium, and it's still 94 protons and still a mass of 245. So these are very simple. And these were our three types of spontaneous decay. Hope you enjoyed the video, you took notes, and if you have any questions, please feel free to ask me during class. Thanks for watching, and we'll see you later.